Hello, and welcome to our presentation on Map901, where we are building rich interior hazard maps for first responders. Firefighter deaths and casualties occur due to navigation difficulties in smoky environments. According to the National Fire Protection Association, in 2018, 64 firefighters and 3,655 people lost their lives, and 15,200 people were injured in building fires. One of the most disheartening facts about firefighter fatalities is how close to an exit the firefighters were found, sometimes less than a mere 10 feet away. High-quality 3D maps are a possible technological solution to reduce these sorts of tragedies. We have surveyed 7 facilities with 1.86 million square feet of indoor space that are of interest to public safety agencies. All the buildings are located in Memphis. Some of the buildings, like the Pink Palace, have undergone many renovations which make it difficult for first responders to obtain accurate drawings. Some buildings, like the Memphis Central Library, have historical artifacts and important documents to protect. Others, such as the Liberty Bowl and Wilder Tower, have a large number of occupants to evacuate in the case of an emergency. This diagram illustrates an overview of our approach. We use our scanner to capture LiDAR data and image data. We run the image data through a machine learning algorithm to produce the annotations. We combine the annotated image data with the LiDAR data using a SLAM algorithm to build the map and a data fusion algorithm to apply the color and annotations from the image data. This gives us our raw point cloud. We then perform clustering and manual cleaning to remove incorrect labels and poor quality data. Finally, because we scan each room separately, we stitch all the scans into a complete building, then use GPS measurements to georeference the final point cloud. To develop our scanning hardware, we modified the Green Valley International LiBackpack 50 to add an Insta360 Pro 2 camera. The camera, like the LiDAR, captures 360-degree images. The user wears the backpack on which the camera and LiDAR are mounted, then controls the backpack with a tablet held in their hand. The tablet also displays the in-progress scan so the user can evaluate it for issues while scanning. We additionally use the Reach RS Plus GPS receiver, which is not shown here, to measure coordinates on the building to perform georeferencing. When we do our data collection, we first plan a route to walk through the space. Because the backpack is not designed for indoor use, it can be confused and generate SLAM errors by, for example, crossing previously scanned paths or walking through doors. Additionally, because the LiDAR is high on the user's back and the vertical field of view is poor, we plan to walk as far away from walls as possible. We also remove humans from the space because they show up duplicated as they move around. Once the plan is decided, the operator walks through the area accordingly and uses the tablet to start and stop the backpack recording. This shows the room scanned in the previous video. The LiDAR sensor on the scanner produces the 3D map, but it does not contain any color or label information. Because we know the physical relationship between our scanner's video camera and LiDAR, we can calculate which pixel of the camera image each point maps to. Then, we transfer that pixel's color to the point. From the requirements collected from first responders and other stakeholders, we have identified 30 high-priority objects which we label in our point clouds. These include objects potentially dangerous to first responders, like hazardous materials and utility shutoffs, items important for navigation through the building, like doors, windows, and elevators, and items important for monitoring and responding to a crisis, like fire extinguishers, fire alarms, sprinklers, and emergency lighting. In order to fully automate the process of identifying these safety objects, we annotated images for training a neural network, which was accomplished by manual annotation using Label Me. To label objects in Label Me, the user can use the mouse to draw a polygon containing an object in the image. For example, in this video, we want to label the fire extinguisher in the center. So we click on a point on the border of the fire extinguisher and continue clicking along the outside edge until we return to the starting point. Once the polygon is closed, we can select the fire extinguisher label for the object. We annotated, on average, about 300 images from each building we scanned. Then, we divided the manually annotated images into training, validation, and test data sets. By annotating the colored images, we can also label the points. Here, the orange indicates exit signs, the green indicates windows, and the yellow indicates people. We developed an interactive cleaning tool using Open3D to enable a user to remove falsely labeled objects easily from a 3D point cloud. It uses dbScan to cluster all the points with the same label into individual clusters, so the users have to deal with only tens or hundreds of clusters instead of millions of points. After the user selects and removes the falsely labeled clusters, the cleaning tool maps the removed clusters to the original point clouds and exports the corrected point clouds. Finally, it merges all the corrected point clouds, one for each point class, into one point cloud. Now, the buildings are divided into hundreds of point clouds, each containing only a small part of the building. The main challenge now is how to stitch these point clouds into the whole building. At this point, we do it manually with the help of Cloud Compare, which is a 3D point cloud and triangular mesh editing and processing software. First, we import two pieces of the building into Cloud Compare and make sure that those two pieces are physically connected in reality. Then, we manually align them as best we can. We repeat this until we get the whole floor, and then do the same thing between each floor. After stitching, we measure the GPS coordinates of several points around the building's exterior. With those points, we use the alignment tool again to georeference the building. We chose the Universal Transverse Mercator WGS84 projection because the point cloud data is in meters already. The georeferenced data can then be loaded into ArcGIS Pro and visualized on a map. Since the point clouds are scans of reality, using virtual reality to view them seemed natural. To do this, we use an Oculus Rift S and the free Point Cloud XR software. The point clouds are scaled up to real size so that 1 meter in the scan represents 1 meter in VR. This enables them to be virtually walked through. With the data presented like it is in reality, examining the clouds is much easier. With the knowledge from watching the video used for coloring, objects and rooms can be easily identified. Inconsistencies and glitches stand out and are easily examined. We collected over 17 terabytes of raw data across all of our buildings. If you wish to use this data for your own research purposes, you may request it through the City of Memphis at the link shown. We have additionally published our work at Smart Greens 2021 in more detail. More information is also available on our website. Thank you for watching our presentation.